Hello people, it's Zach here again today, and this video is going to be about special relativity, so it's going to be involving a little bit of math, but it's nothing too complicated. If you've taken third grade, you'll probably be able to follow along just fine. So let's go ahead and just jump right into this. So the problem that we're going to be working on, we're going to be assuming that I have this really fast car, and my car is traveling in a straight line from the left to the right here, and this line is actually going to be parallel to a brick wall that's back here. Now what we're going to say is that at some time, I'll just call it t sub 0 or whatever, I'm going to honk my horn, and by the nature of sound, this sound is going to be traveling out in all different directions. Now let's just say that in the time it takes for the sound to get from here to this back wall, my really fast car has traveled from here to here. Now, so what this means is my fast car moving at a speed of v for some period of time t0 has traveled this distance, and in the exact same amount of time, t sub 1, traveling at the speed of sound, the sound has traveled this distance. And so, as you can see here, we've got a right triangle. And the question is, what is this distance? Well, knowing the speed of sound, we would know that it would take some certain amount of time. We don't know exactly what time, t sub 2, to travel this distance. So obviously the length of this line would be c times this t sub 2, which we don't really know. So how do we solve this particular problem? Well, we can start by using the Pythagorean theorem. So we know that v t1 squared plus c t2 squared is equal to c t1 squared. Now, we'll go ahead and just distribute all of these exponents, and we'll get v squared t1 squared plus c squared t2 squared is equal to c squared t1 squared. Now, see, we got a t1 squared here and a t1 squared here, so we just go ahead and divide everything out here by t1 squared. And what we're going to get is v squared plus c squared t2 squared over t1 squared is equal to c squared. Now we see we got a c squared here and a c squared here, so let's just go ahead and divide everything out by c squared. And what we're going to get is v squared over c squared plus t2 squared over t1 squared is equal to 1. Now what we're going to do is we're going to take this term right here, we're going to move it over to the right hand side. So we got t2 squared over t1 squared is equal to 1 minus v squared over c squared. And now we're just going to take the square root of both sides. We get t2 over t1 is equal to the square root of 1 minus v squared over c squared. And now this term right here, we're going to call that gamma. So we're going to gamma is equal to t2 over t1. Now, by the definition of gamma, what we see is that t2 is equal to gamma t1, which means that this distance right here, c t2, is going to be equal to c gamma t1. So now, knowing this, if we know how far we've traveled, or how long we've traveled, we know exactly how long this line is. And so this gamma term right here actually just kind of like a coefficient that allows us to go from, convert this time right here, this t1, into this time right here, t2. Now, question then is, well, what does this have to do with special relativity? Well, here's the thing. This gamma term right here that we've defined, as t2 over t1, which is equal to the square root of 1 minus c squared, 1 minus v squared over c squared. This is called the Lorentz factor, and it's used in special relativity to determine what they call time dilation or length contraction or relativistic mass. But the thing is that like this c squared term right here, this is just the speed of induction for the field. And this v squared term is just like your regular speed is for an object moving in this field. And what I think is absurd about this is that if they're trying to say that, well, as you're approaching the speed of light, that this is going to cause your time to dilate or your length to contract or whatever, or your mass to go to infinity, that's absurd, because by the same exact logic, when you approach the speed of sound, the same thing should happen, because according to this equation right here, it's the same exact equation being applied the same exact way. And so what this is really about is the fact that you're trying to measure distance right here in terms of the speed of the field that you're dealing with. The idea that your mass is going to infinity, or that your length is contracting, or that your time is dilating is not real. It is a perceptual effect, but it is not a real thing. Your mass is not actually going infinite. Your length is not actually contracting. Your time is not actually dilating. And see, like this would be a simple thing as well. Like if you consider like if an object was moving super, super fast in this particular direction, and say for example, my eye right here is watching this thing move by. Well, if it gets really, really close to the speed of light, what ends up happening is that my perception of this thing kind of gets squeezed, because by the time that that I'm seeing the light from, like here, it's already moved, and so this is where you start running to the perception of like length is contracting or time is, or whatever, that's all that is. Like I said, it's just not real. Now, there's just one more thing I'm going to add on here because I thought this was kind of interesting. So, if you've ever seen the definition for the speed of light, it comes to c is equal to the square root of 1 over mu sub naught epsilon sub naught. Now, we can rewrite this. We can say that c squared is equal to 1 over mu epsilon sub naught, just like this. Now what we're going to do is we're going to divide both sides by c and multiply both sides by mu sub naught. And what we're going to get is this right here. C mu sub naught is equal to 1 over c epsilon sub naught. Now what's interesting about this is if you've ever seen LC circuits, there is this thing called reactance of the circuit, and the inductive reactance, which is X sub L, is equal to the angular frequency times the inductance, and the reactive capacitance is equal to 1 over the angular frequency times the capacitance. And the thing too is that this inductance, of course, that is a magnetic property, just like you have the magnetic permeability here, and this capacitance is a dielectric property, as is this dielectric permittivity right here. So you can see there's this parity here between reactances and the speed of light equation, which I just thought was really amusing. And I'm kind of curious if that kind of suggests something about the nature of light that just hasn't been considered before. But as well, I mean, if you're talking about the impedance of a circuit, what they call the complete reactance is actually this X of inductance minus the X of capacitance, which is like, of course, your angular frequency L minus your 1 over your angular frequency C. And if we were to apply this exact same thing to this up here, and we said, well, C mu sub naught minus 1 over C epsilon sub naught. If you work out what this actually is, it comes out to, it's like something like around 6.1035 or something like that. Of course, I don't think these are any sensible units at all, because of course you're trying to, the units for this is different from the units of this. But I just thought that this was an amusing thing that people might find Maybe this has some significance to it. I don't know. But anyways, that's pretty much it. Thanks for watching.